So far in the course, we've been evaluating limits by using the limit laws. So that involves a whole bunch of stuff, but for the most part, it's sneaking a peek. And we would often encounter the forms 0 over 0 or infinity over infinity. These are called indeterminate forms. And our method was to use some algebra to try to rewrite these limits and evaluate them. So for example, if we take a look at this first limit going out to infinity, if we were to sneak a peek in this case, we would see some sort of infinity over infinity. And in the second case, same idea. If we were to sneak a peek, we would see a 0 over 0. Now, in both of these cases, we would say, all right, no limit laws, time to do some algebra. In the other examples that we had looked at, it was fairly clear what algebra we should do. There were things like common denominators, rationalizing, conjugates, all this sort of stuff. But in this case, the algebra is unclear. What do we do when we have a transcendental function like a logarithm or a log of a log, etc.? In this case, it's not clear what the algebra should be. So how do we evaluate these limits when we don't know what algebra to do? So there's going to turn out to be a new rule that we will talk about. And this is something called L'Hopital's rule. And it's for indeterminate limits. So limits of the form 0 over 0 or infinity over infinity. And it's a rule that's going to involve derivatives to help us get to the limit answers we want. So I'm going to take a look at the case of 0 over 0. I'm going to prove it for the 0 over 0 situation. And in this situation, it turns out can be modified easily to get the infinity over infinity case. So to try to understand what we're talking about, so suppose we have a limit of this form, and if we were to sneak a peek and see a 0 over 0, this is a 0 over 0 type of indeterminate form. Now, just to remind you what this means that when I plug in the value of the limit a into the function, on the top it gives me a 0, and when I plug in the value of the location a into the bottom function, it also gives me 0. So I'm going to try to proceed in this way by taking use of that fact. So what I mean by that is, if we were to then take this limit, we could then very simply plug in an f of a and a g of a in this way, because in each situation, both of these things are 0. And as soon as I see this f of x minus f of a and g of x minus g of a, I think to myself, aha, this starts to look an awful lot like a derivative. And so what's going to happen in this particular case is that I'm going to make an assumption. I'm going to assume that the functions f and g are differentiable at x equals a and on some interval that includes x equals a, so near x equals a as well. And in that particular case, it means that if a function is differentiable, it also means that the function is going to be continuous. So all of these assumptions here are going to help us. And now we go ahead and we say, okay, I'm going to try to rewrite this limit so that it looks like it contains derivatives. And in particular, I am going to rewrite this and put an x minus a in the denominator of both limits. That's completely reasonable because x will never get equal to a in a limit. We just get closer, but never there. And we are doing the same thing to the top as we are in the bottom. And so because both of these functions are differentiable, what that allows me to do is that I can say that the limits exist and I can apply the limit laws. So I'm able to split this up into the limit of the stuff upstairs, which is just the derivative of the function f at the point A, over the limit of the stuff downstairs. Now, as soon as I get downstairs, I have to be a little bit careful here. I know that the function is differentiable, which means that the derivative exists. I am also going to assume that the stuff in the bottom is never 0. So I'm going to assume that g prime is not equal to 0 at x equals a and near x equals a. So it's a little bit of a specialized situation, but you can see that it's a reasonable thing to assume here. So at this point, what I'm allowed to do is simply treat the top as an f prime of a and a g prime of a. Now, this may or may not help me. It's good my assumption will kick in here so that the thing in the bottom isn't going to be 0. But I'm going to make one last assumption to try to help my situation out here, and in order to build a rule. I'm going to assume that the functions f prime and g prime are continuous at x equals a. And if those functions are continuous at x equals a, by definition, if a function is continuous at a point, that means the value of its limit is the same as the value of the function itself. And so what I get to is that every time I see an f prime of a, I could replace it with a limit. And every time I see a g prime of a, I could replace it with this limit. So at the end of the day, I can replace the numerator with the limit of the function f prime of x, and I can replace the denominator with the limit of the function g prime of x. Now you might say, oh, this assumption is too strong. We're assuming a lot of things. And this is true. But because there turns out to be a more rigorous, less a form that uses fewer assumptions, so it will turn out that this is possible. I'm just trying to show you a way that uses the tools that we've already got to try to help us out. The other thing here is that I'm going to say they're continuous at x equals a and near x equals a. And so in this particular case, we are set, and we can go one last step. We can take this, and because the functions are differentiable and continuous near x equals a, all the limits will apply, all the limits exist. We've assumed that the denominators aren't 0, so all the limit laws can still apply. And what that means is if I have the limit of some stuff upstairs divided by the limit of some stuff downstairs, I can combine them into a single limit. And at the end of the day, here's what I get. Again, this is what's called L'Hopital's rule. If I'm ever faced with a limit of two functions, and they give me some sort of 0 over 0, I am allowed to say that it's equal to the limit of the ratio of their derivatives. And to let my poor teacher know that I'm trying to do this, I'm going to put a little h above the equal sign just to denote that, oh, I am invoking L'Hopital's rule here, and it works. So it only applies to 0 over 0 or infinity over infinity indeterminate limits. And it's kind of reasonable. Remember that if we have differentiable functions, when we have two functions, let's say that their limits are going to 0 over 0. So if I have two functions like this, f and g, and both of them approach 0 at this location A, if I were to zoom into there, the closer I get to a differentiable function, the more and more they look linear. And so what's important here is not so much the functions themselves, but their slopes. And so it's going to tell us something about the value of the limit by evaluating how fast they get there, talking about each of their slopes and the ratio of their slopes. So L'Hopital's rule is really useful. In particular, if we evaluate those limits that we talked about earlier, and we say, oh, this is infinity over infinity, both of the functions are differentiable. I can use L'Hopital's rule. So L'Hopital's rule says take the derivative of the stuff upstairs, take the derivative of the stuff downstairs, and then evaluate the limit of those individually. So the stuff downstairs is very easy. The derivative of x is just 1. The derivative of a logarithm of stuff. According to the chain rule, it's 1 over stuff times the derivative of that stuff. And so if I just continue on here, I'll end up getting 1 over x times 1 over the natural log of x, all over 1. And this could be written as 1 over x times the natural log of x. And so once you apply L'Hopital's rule, it's almost like it resets. It gives you a new limit. So once you think you've hit the end of the road with your limit, it's time to sneak a peek again. And when x gets really large, both of the things in the denominator get really large. So this gets to a 1 over infinity. Now I can't use limit laws because the limit in the bottom does not exist. So I'll have to talk about this analysis stuff. And what I mean by that is as x goes to infinity, the numerator goes to 1, x goes to infinity, natural log of x goes to infinity, and their product also goes to infinity, which is just some sort of large number. Now, together, they go to 1 over some very large number, which goes to 0. And in this sense, the limit will be 0. I like to think of L'Hopital's rule as a statement, like a race. When somebody asks you to evaluate a limit, they are asking you something about who is finishing this race first. And so you know that because it goes to infinity over infinity, both functions end up in the same place. But to see who wins the race, you need to see who crosses the finish line first, who becomes large first. If the function on the top gets very big, much, much quicker than the function on the bottom, then the whole limit would go infinite. If the function on the bottom gets really, really big, much quicker than the function on the top does, then the whole thing will go to 0. And that's in fact what we have here. The function, L'Hopital's rule is telling us that because the limit is 0, this whole function, the term on the bottom, grows much quicker than the term upstairs. If you end up with some value that's neither 0 nor infinite, that means the functions grow at some sort of comparable rate. In this case, what we are seeing is that the function in the bottom gets to infinity much, much quicker than the one on the top. If you want to see who wins a race, you have to be at the finish line, not hours after everyone's finished, but right as they cross the line. You need to see who gets there first. And in some way, that's what L'Hopital's rule does. It puts you on the finish line right as the racers are coming in. Now, you can do the same thing here. If you were to take a look at this limit, L'Hopital's rule only applies when you've got 0 over 0 or infinity over infinity. So I am going to use the rule here. And what it tells me is that it's going to be equal to the derivative of the function upstairs divided by the derivative of the function downstairs. That's the only time I'm using the rule. I end up getting a limit of 1 over x, which just ends up giving me a 1. This result tells me that the functions both approach 0 at the same rate, exactly the same rate. That's why the ratio of their derivatives, the limit is 1. And so L'Hopital's rule now is this final tool that we have for evaluating limits. Sometimes limits are difficult to do with algebra. Sometimes they're not. Students love L'Hopital's rule because they think it allows them to just ignore everything they've ever learned about limits. This isn't the case at all. Sometimes L'Hopital's rule will work really well. Sometimes it won't. So for example, if I were to sit here and say, oh, look, here's this limit. If I were to sneak a peek, I'd see infinity over infinity. Oh, I'm going to use L'Hopital's rule. And if you use L'Hopital's rule, you'd take the derivative of the top. So you'd get a 1/2 x squared plus 2 to the negative 1/2 times 2x. Those would go away. And downstairs, you'd get a similar thing. 1/2 2x squared plus 1 to the negative 1/2. And you'd get a 4x here. So this 2 and that 1/2 would go away. And you'd rewrite this limit, and you'd see it as x over that square root divided by 2x over this other square root. So these x's will cancel out, and you'd be left with a limit as x goes to infinity, 2x squared plus 1 root upstairs, and then the other stuff downstairs. 2 times this other root. Now, students just like to plow through. L'Hopital's rule's got to be able to do it. So I'm going to sneak a peek again. I'm going to see infinity over infinity. Well, what you're going to find is that if you use L'Hopital's rule again, you're going to get a similar situation to what you had before. You take the derivative like a good student, and you get a 4x up here, and a 1/2, and an x squared plus 1 to the minus 1/2, 2x down there. And what's going to end up happening is you're just going to end up getting similar expressions to what you had before. These roots don't ever go away. They just hang around. Yeah, you're going to get some strange factor, but the point of the story is that L'Hopital's rule will not take you anywhere here. What you should be doing is the stuff from chapter 2.6, where you should be rewriting everything in terms of 1 over x. So don't get too comfortable with L'Hopital's rule. It's great. It can help you, but it won't get you out of every